Let's see if this likes this. Otherwise, it might have to switch. Okay, there we go. So the motivating example would be something like this when we're talking about matched pairs. Okay. It would be something like, I have a manager and maybe they, rearrange the workstations, or they, made some change to the office, and they want to know, did it have some effect on productivity of the workers, right? So I might have the same 10 workers, and instead of comparing like the sample means from two different samples, right? Two different samples of 10 people, it's the same 10 people. It's just that what I'm doing, right, is thinking about, so let's say I've got different employee IDs, these could be whatever we want them to be. This is just using, numbers instead of their actual names. We would then have their after and before productivity measures. So it's almost like we have two variables for the same 10 people. So maybe it looks something like this, something like this, like here, and then, I don't know, 15 from 12. So what we're going to do, instead of finding the average productivity before and the average productivity after, and then like looking at the difference between those, we're actually going to calculate within each individual. So it gives us a little bit more power, because here we're almost like controlling for the fact, like all these other characteristics that we can't observe about the individual, right? If I have two different samples, I don't know what characteristics are different about those different two groups of 10 people. Here, I know that if I calculate the difference for every single employee, I'm doing it like within employee. So I'm kind of controlling for the characteristics of whatever are specific to that employee. So here, I would say, okay, before to after productivity went up by 2, the change for this employee was 5, -1, and then 3, so on and so forth. Then what I can do is find my average difference, right? What was the average change per employee? Okay. So if we think about what I'll have here, we're going to call the average of this difference variable. That's going to be my sample difference. It's essentially found the same way that we found sample means, right? It's just now we're going to have a sample difference. So the notation is a little bit different, but it's just because we have to somehow indicate that the mean that we found came from this difference variable that we created from 2 other measures, right? So that's all that's really the only difference is the notation there. Well, and we had to calculate this difference variable. But then when it comes to things like confidence intervals, just like with one population, I'm going to look up the t-value that tells me the number of standard deviations away to the left and the right I need to go to build my confidence interval. And I'm going to multiply it by the standard deviation of whatever statistic I'm looking at. So here, the standard deviation of my sample difference is going to look just like it did with one population examples. It's just the sample variance that I now have is a sample variance coming from this difference variable, right? So I'll use this difference variable that I created to calculate my mean difference and to find the variance of my sample. And then I still need to divide by my sample size. But it's really following kind of the same sort of format. And what's nice about these matched pairs examples is because it's the same sample, my degrees of freedom goes back to simply being n-1. So I don't have to use that crazy complicated formula. I just can go back to what it was for one population when I only had a sample variance, which is just n-1. So hopefully we can kind of see the connection to like what we've done already. It's just got this added step of calculating this difference variable. Now I'll kind of walk through a couple Excel examples. I think it makes a little more sense when you see it done in Excel, but we'll work through a few examples just to kind of get used to it. Work through a few by hand first, okay? So, oops. Let's see if we can try this one more time. See if it freaks out. Okay. I'm not trying to give anyone a seizure here, so we will. Oh, all right. So all right, we're not going to be able to use presenter mode on this computer apparently. So we'll go back to just look at the slides as I walk through these. So I won't be able to show you things step by step, but it should be all right. So we already had this kind of written down. Sometime there we go. But here's my confidence interval equation, right? So really, these confidence intervals shouldn't be that difficult. We'll kind of see the problems we work through. We're given the mean difference, we're given the variance, we're given the sample size. Really, it's just a matter of kind of getting used to looking up these t-values, okay? So we'll go to this kind of first example and I'll kind of walk us through it. Right? So once again, I don't know why this isn't liking presenter mode up here. I've had that happen occasionally, but it looks like today we won't have the presenter mode. So I'll show this to you all at once. So let's say that manager who had the 10 employees goes through, finds the difference for every employee, finds the mean. So they find a mean difference of 8.5, and then they found a variance of 121. And they want to build a 95% confidence interval. Well, this is where, if you've got that formula sheet in front of you, right, if you can't remember it, which you might not be able to remember all these, you're basically just plugging your values in. You've got the sample difference of 8.5, the variance of 121. You've got the sample size. If we go back, right, it was 10 employees. So we'll plug in sample size of 10. The only other step you have is to look up that t-value. So why is it 2.26? Like I have it here in the slides, but why is that the case? Well, if I want a 95% confidence interval, my alpha is what? Yeah, 0.5. So hopefully I haven't forgotten too much over break, right? So it's going to be 0.05, right? That's the area outside my interval in decimal form, right? 5% would be outside the interval, decimal form, 0.05. However, I have to divide alpha by 2, right? My formula kind of reminds me of that. So the area I want in the tail is 0.025. Right? My degrees of freedom, if I had a sample size of 10, goes back to simply being sample size minus 1. So my degrees of freedom would be 9. So now I'll go, I think it's in the main folder here. I'll open up my t-tables. Oh, there it is. The area I wanted in the tail was 0.025, and my degrees of freedom was 9. So 2.26 should be the t-value that gives me that desired area on each side of my confidence interval. Right? So when you're looking up these t-values for confidence intervals, it's very much like when we looked up critical values for two-tailed tests. Right? You just divide alpha by 2, figure out what your degrees of freedom is, and then kind of where do those two line up. Here, that would be at this 2.26 or 2.26 value. Okay. So that's how I found that t-value. Once I have that, I've got everything I need. It's just a matter of getting this plugged into my calculator. Okay. Any questions over any of the steps there? So what could I say with 95% confidence about the average change in, or the average difference in productivity here? With 95% certainty, I could say, yeah. Not only that clearly there was a change, I could actually say that clearly there was a change, and clearly the change was positive, right? Because I only have positive values here. I'm thinking about, I think it was like what, 0.6 to, I don't know, something over 10. So we'll just say 10 for the sake of it, right? This is the range with 95% confidence. I'm saying the true mean difference, right? Or if I could observe this population mean difference, it's somewhere in this range. Well, if all these values are positive, then that means with 95% certainty, I can say that that true mean difference, that true change in productivity is positive, which implies if I did after minus before, if I can talk and write at the same time, if this is a positive value, the only way that's possible is if productivity increased, right? If productivity is higher after the change than it was before. So because I only have positive values here, it kind of allowed me to make a statement about, you know, this specific application of matched pairs. I could say that with 95% certainty, that difference is positive, which implies productivity increased. Okay. Any questions there before we keep moving? Okay with that? All right. So the next thing that we can do, if we can build confidence intervals, we can do hypothesis testing as well. Right? So we're going to have the same 3 types of tests, right, left, two-tailed tests. It's just now, instead of a regular mean, we're thinking about the mean difference. And we're going to have, is it greater, less than, or not equal to some assumed true value? Now, just like with the other 2 population examples, because more often than not, we actually want to use a 0 here, I'll always give you on the exam, there might be some on the homework where that assumed true difference, right, D0 there, subscript 0, that might not be 0. So on the connect, you got a little more time. I think that potentially or expect that you could work through those, right, with something other than 0. On the exam, just like with 2 populations, I'll always use an assumed true difference here of 0. Okay. That makes sense. Okay with that. So my test statistic becomes this right here, but we can kind of, just to kind of make the comparison, because I think it helps to see that really what we're doing with hypothesis testing confidence intervals is really following the same set of rules. So when I was looking at a sample mean, to come up with that test statistic, which remember, it's a t statistic only because it's a test statistic coming from student t distribution. Right? So I'm going to take that sample mean, subtract the assumed true value for the population mean, divide by the standard deviation of the statistic I'm interested in, which we said was the square root of the sample variance over my sample size. Same kind of idea for this sample difference, right? I'm going to take the statistic I'm interested in, that I saw from my sample, subtract the assumed true value of that statistic, and then divide by the standard deviation of that statistic. Okay? It's just now, right, a little bit difference in notation. I can use a subscript to indicate that this variance is coming from a difference variable I created. But other than that, I mean, once I plug these values in, it's going to look no different than what we were doing with a 1 population example. Okay? So my test statistics should look very similar to when we had a 1 population sample mean with only a sample variance. Okay. So that's our test statistic equation that we can use to kind of start do some hypothesis testing. Okay. So let's go back to this example we had and try to do some hypothesis testing with it. Well, now, before we even get started, all right, we said that the true difference should be positive. So if I'm going to do a hypothesis test for the value of 0, right, it should be I can reject that value of 0 if I was to do a 2-tailed test. Now, if I do a 1-tailed test, it could be a little skewed, right? Because I'm kind of like shutting down one side of the distribution. However, it should be a very similar conclusion that I get from my hypothesis test as I did with my confidence interval. And if my confidence interval doesn't include that value of 0, well, then I would expect with my hypothesis test, I could reject that as a possible true difference, right? Or if I assumed that was the true difference, I could just reject that. So we'll work through it and hopefully those kind of things line up. So let's say, actually, did I skip through this? There you go. So let's say that instead, I want to do some hypothesis testing. Well, the easy question should be, what is the test statistic? So once I have that equation in front of me, this should be the easy part. I plug in my sample difference, plug in my variance, sample size, we had 10 workers. The assumed true difference we were going to use is 0. So for us, just to get some practice, I'm going to do a 2-tailed test here. Okay. So let's say we want to do a 2-tailed test. Right? And we've got our test statistic. That should be the easy part. It's just a formula. We're given the values. We just need to plug them in. So we get this test statistic of 2.44. We've got 2 approaches that we could use. The first one I'll go through is the critical value approach. So I think it's a little bit easier when we're dealing with situations where we have to use the student t distribution. So if I'm thinking about the distribution of my sample differences, just like with my sample means, they should be centered around whatever that assumed true difference was, which we were using just 0. So I'm going to set this up as a two-tailed test where I'm just going to say, is that difference anything other than 0? So I assume the opposite is true to stack the deck against myself, which is that it is exactly equal to 0. I found a sample difference of what? It was like 8.5, I think. So then what I did was I determined how many standard deviations away from that assumed true difference is the sample evidence that I found. The number of standard deviations away, well, that's just my test statistic. Right? It represents how far away from that assumed true value my sample difference was. Once I have that test statistic, I can find the area to the right of it. Now, if it was a right-tailed test, this would represent my p-value. But because it's a two-tailed test, it would have been equally as likely for me to see a sample mean difference on the other side that would have also went against my null hypothesis. So whatever area I find here, that's really only half of my p-value. So we said to get my total p-value, I need to do what? Two-tailed test, I can find the area in this right tail, and then I have to multiply it by 2, because it only represents half my p-value. So if I multiply it by 2, notice this cancels and I get just left with my p-value there. So we want to look up kind of what this area is and this area is to get our p-value. The problem is going to be for a student t-distribution, I might not be able to find an exact value for my p-value. I might only be able to put it in a range. Okay? I think I said initially I was going to start with the critical value approach, and then I started talking and I talked myself into the p-value. So here we are at the p-value first, I guess. And then hopefully we'll see with the critical value how much easier it is. So I go to my student t table. My degrees of freedom, this is with 10 workers, so I still have degrees of freedom of 9. And I'm going to look for this value of 2.44, which was my test statistic, and I can't find it. Right? There's only 6 values up here. However, I know the area to the right of 2.26 is 0.025, and the area to the right of 2.8 is 0.01. So 2.44 is somewhere in the middle of these two. So if I can find the two values that I'm in between, I said that for that 2.26, that gave me an area here, which was 0.025. And then for the value of 2.8 something, the area to the right of that was 0.01. So if I'm looking for the area to the right of my test statistic of 2.44, well, it's going to be less than 0.025, but greater than 0.01. So all I can really do is say that my p-value is somewhere in between, or sorry, I shouldn't say my p-value. The area in this right tail, right, which is half my p-value, is somewhere in between 0.01 and 0.025. Now, I won't expect you to do this on the exam. On the exam, I would have given you a test statistic that exactly worked out to be one of those 6 values on that student t-table at that degrees of freedom of 9. However, I think on some of the homework problems, they might have you where they ask you for what the range of the p-value is. And this is really how you would do it. You find the two t-values that your test statistic is in between. And so then you know that the area to the right of your test statistic is somewhere between the area to the right of whatever two t-values it was in between. Okay? But on the exam, I would have to give you a test statistic that's exactly a number in the table. I won't expect you to kind of put it in a range here. Now, this one makes it a little bit harder in that that's just the area in one tail. So if I want to put bounds on my entire p-value, well, if I know this area is in between 0.01 and 0.025, and this area would then be in between 0.01 and 0.025, all I can say about the total p-value is it's somewhere in between 0.02 and 0.05. Right? Or basically, once I can put bounds on one of the tails, because they're exactly the same size, right, symmetric distribution, I would just multiply kind of whatever those bounds were that I put on it by 2, just like I would if I, could find the exact area in that tail and not have to put bounds on it. Okay. So this is, the student t distribution makes things a little bit tricky, or trickier, I should say. Are there any questions? I know that I kind of punted on this when we were doing one population stuff in terms of putting the p-value in a range, but I wanted to kind of point out how we could put it in a range if I expected that out of you on the exam, or if you have to do it like on your homework.
So what is this saying in terms of like our hypothesis?
Yeah, so that's the next step, right? If this is where my p-value's at, okay, well, then at what levels could I reject that null hypothesis? So let's see if I can solve the same. There we go. Well, my p-value, I only reject the null if my p-value is less than alpha. So if my p-value is somewhere in this range, is it going to be less than, say, an alpha of 0.1? Well, if it's somewhere, if it's less than 0.05, it's definitely going to be less than 0.1. So I can reject at the 10% significance level. Is it going to be less than an alpha of 0.05? Well, if it's somewhere in this range, being less than 0.05, then it's going to be less than 0.05, right? So I'm rejecting that null. I'm rejecting this assumed true value of 0, which at the 95% level, I should have been, at least if it lines up with my confidence interval, right? Because 0 was not one of the true population values based off my confidence interval at the 95% level. Okay. But now notice what happens if I wanted to instead go to the 99% confidence level or the 1% significance level. Well, if my p-value is greater than 0.02, it can't be less than 0.01. And so I would fail to reject the null at the 99% level. Okay. Now that shouldn't matter. The confidence interval we did was at the 95%, so we can't really compare those, but we should be coming up with the same decision based if we're at the same level of confidence, which we did. With 90 and 95% confidence, we can reject the null here. With 99, we couldn't, right? With 99% confidence, I couldn't actually say that based off the sample evidence I found and the sample size I took, that true difference is anything other than 0. Which 95% confidence is still pretty high, right? Does that answer your question? Okay. Any other questions on this before we look at the critical value approach here? All right, so let's say I want to do the same exact problem, right? But instead, I want to look at my critical values. Okay? So for a two-tailed test, right, at every single alpha level, I'm actually going to have a pair of critical values, right? So I'll have critical values that give me a total area of 0.1 in the tails, which means that in each tail, I would have half of that, right? So you can kind of think about, this would be 0.05. I then have a pair of critical values that give me 0.05 total in my tails, which mean in each tail, there's only half of that, so 0.025. And then if I save myself enough room, there's critical values that give me an area of 0.01 in the tails, which would be an area of 0.005 in each tail. Right? So this is just going to be like a cutoff number of standard deviations away from that assumed true value. If my test statistic is any further than this cutoff number of standard deviations, then I'm okay rejecting. So we kind of, usually the way I draw this is like arrows that go into the tails that kind of signifies this is like my rejection region. My test statistic falls in these regions, I can reject. If not, I fail to reject. Okay. So we can look those up because we just said the area that we want in each tail, right, in the upper right tail and in the lower left tail was half of alpha. So that became 0.05, 0.025, and 0.005. And those are the areas that I want in the upper right tail. Right. So I go to my degrees of freedom of 9. And I say the area that I want in the tail was 0.05. So this is going to be what? 1.833, 2.262, and 2.821. And then those same values on the other side, but negative. I ran out of room here, so this one's going to have to go down here. Okay. So I look at my degrees of freedom. I look at those three kind of confidence or significance levels I wanted to get my critical values. And now I've got my critical values with the rejection region. So the critical value approach gives you a little bit nicer of a visual here. Because now when I go, I just plot my test statistic of 2.44. That would be somewhere about right here. That was my test statistic. So at the 10% level, 5% and 1%, my test statistics in the rejection region here. At the 5% level, it's in the rejection region, so I reject. But at the 90 or the 1% significance level or the 99% confidence level, I'm not quite in that rejection region. So I come up with the same conclusions that I did using that p-value approach, right? Same conclusions, reject at the 90 and 95% confidence levels, but not at the 99. Okay. Any questions over any part of that process? Okay. So there's no questions. Keep on going. So here, I'm not going to waste too much time on this. It's just another example for confidence intervals. Really, the only tough part of this, I think, or the thing we probably just need more practice with, is looking up these t-values. So let's say I have, I don't know how long ago it's been now, 10, 20 years, something like that. Like I remember, I don't know what it was, but I know there was some point where they made a big deal that fast food places started putting calories on their menus, right? So maybe a reasonable question would be, have people consume more or fewer or any kind of different amount of calories since companies started doing this? So here, what we want to test, we're going to look at the same 40 Starbucks customers, right? We can track their orders across time. And we're going to calculate what their calories consumed were in their orders before they posted the calories and after. For each person, we'll find the difference or the change in their calorie consumption. And then we could calculate an average difference, and we could calculate a variance from that difference variable. If I wanted to build a 99% confidence interval, well, first of all, it should be centered around that sample difference of 2.1. Looks like all of these on an eye test pass it, right? Looks like 2.1 is pretty much smack dab in the middle of all these, so we can't rule anything out. From there, it's just a matter of, I've got my confidence interval equation from before. I just need to plug all my values in. So go back here, right? Here is my general form of my confidence interval. I had 40 Starbucks cardholders, so got my sample size. I was given the variance. I forget what it was now off the top of my head. And I think we found a sample difference of 2.1. So the only other thing we need there is that t-value. So if I want the 99% confidence level, my alpha is what? 0.01. I need half of alpha on each side of my interval. So 0.005, right? 0.01 divided by 2. So 0.005 is the area in each tail I want. And my degrees of freedom, if I have a sample size of 40, would simply be 39, right? Sample size minus 1. So I want 0.005 in that tail. My sample size was 40, so my degrees of freedom is 39. So 2.708 is that number of standard deviations away I need to go when I'm building my confidence interval. Or why am I looking at this wrong? Because I skipped ahead. Sorry. 2.708, right, was that t-value that we just found. Okay. So from here, it's just a matter of plugging in our values and getting our lower and upper bound, right? And then I was going to wait and reveal this, but since we can't use presenter mode, I'll take the time now. You guys haven't seen Napoleon Dynamite. You all should. It's a very dumb movie, but it has some great like one-liners. And I have a pretty good Kip impression, but I don't do it in class. So if you've seen the movie, you know how embarrassing that could be. So we've got this lower and upper bound. What can I say about calorie consumption here after Starbucks posted the calories on their menu? If I look at that confidence interval, it goes from negative 1.3 to 5.5 about. So yeah, at the 99% level, I can't say anything. Why can't I say anything? Well, if this is the range of values where that true mean difference is, that difference could be negative, which would imply that if I'm looking at after minus before calories, right, that's how I'm calculating. I did the same thing earlier. That's how I calculate this like difference variable. If it's negative, the only way that's possible is if they were consuming more calories before. One of the true values could be positive, right? Up here, if that difference is positive, that would imply calories after the change were higher. One of the values in this range is also 0, which would imply there's absolutely no change in calorie consumption, right? So based off the sample evidence I found here, at least at the 99% level, I can't say whether or not calorie consumption increased, decreased, or even it might have stayed the same. Now, if I think about the equation I have for my confidence interval, even though I can't say this with 99, what would the argument be for why potentially I could say that calorie consumption has increased at the 90% level? Well, if we think about what we're doing there, if I'm going from the 99 to the 90% level, what's happening to alpha? Alpha is actually getting bigger, right? 0.01 to 0.1. So now if I want a larger area in my tails, what's going to happen to that number of standard deviations away that I need to go? That t-value will actually get smaller. So if my t-value gets smaller, if I go to build my 90% confidence interval, it should be a little bit more narrow, right? So maybe, probably not based off the numbers I'm seeing here, but it's possible that when I go to build this 90% confidence interval, as opposed to the 99, so here was like my 99% numbers, maybe I can get it narrow enough at the 90% level where it only includes positive values, right? And it would still be, if I could say something with 90% confidence, that's nothing to, ignore, right? It's a pretty high level of confidence. It's just not like the highest level. Okay? Kind of just reviewing that, thinking about things that would kind of change that width of our confidence interval. What are questions on that before we keep moving here? All right, so I've got one more here. We'll think about, let's say we have the same setup, but we want to test, and obviously you can see the answers here because I'm not using present it. But let's say we want to test for whether or not calories have decreased. And I said this before when we were doing two population stuff. Anytime you have before and after time periods, you always want to take like the most recent or the after and subtract the older time period or the before. So when we're looking at this difference variable, it's always going to be set up as kind of this after minus before if we're doing something with time. Okay? So if I'm thinking about has calorie consumption decreased, that difference would have to be less than 0. So that's what I wanted to test for. So that became my alternative hypothesis. Whatever I'm testing for, whatever I'm trying to find, that's my alternative hypothesis. I assume the opposite is true, which is that true difference is greater than or equal to 0. So I could go through, find critical values and find p-values here, but why can I avoid that entire process if all I'm trying to do is decide whether or not I reject or fail to reject the null? So if I look at the sample evidence I found here, I think it was on the previous slide, so we'll remind ourselves. I found a sample difference of 2.1. So if I'm looking at my null and alternative hypothesis, a sample difference of 2.1 actually supports the null, right? It's a sample value that is above or equal to 0, right? It's greater than or equal to 0. So if I find evidence that supports the null, why would I be rejecting it, right? So anytime I find evidence that supports the null, I instantly know I should be failing to reject. Excuse me. Now I could go through the whole process. I could look up my critical values, plot my test statistic, but what I'll end up finding out is that I would fail to reject at all levels because I actually found evidence that supports the null, right? You kind of think about it this way. If I've got what type of tailed test here? So I look at my alternative hypothesis. I've got a left tail test, got a less than sign in the alternative hypothesis, so left tail test. So automatically I know my critical values have to be what? Negative, okay? So we're thinking about why, when I'm looking at my student t distribution, it's centered around 0. So if I'm dealing with the left side of the distribution, my critical values will all be negative, right? So I can find those critical values, have my rejection region, and then plot my test statistics, okay? So let's look up those critical values. So my degrees of freedom is 39. So I go down here, 39. I've got a one-tailed test. Now alpha is the total area in that lower left tail. So 0.1, 0.05, and 0.01 are kind of three benchmark alphas. 1.304, I'm going to write these down as I say them, so when I switch over, I don't forget. 1.685 and what? 2.426. However, it's a left-tailed test, so it's going to be those same three values, but negative, right? So now I've got my critical values plotted. So what do I need to kind of plot next to determine whether or not I can reject the null? My test statistic. Okay. So hopefully this won't be too bad for you guys. But if I had that same setup, right? Which of these values would be my test statistic? So we've got, oh, I didn't even, there we go. Let me get this pulled up. So in fact, just to kind of test where our understanding is of what we're doing, on this one, you can go through and find the exact value if you want. We had our equation earlier. Where did I have that written down at? Right. So we have this equation that will give us our test statistic. And if we remember our null alternative hypothesis is that we're assuming it's greater than or equal to 0, right? So based off the sample evidence I found, I'll actually give you credit if you just, there's two of these that you should be able to rule out. So as long as you don't answer with one of those two, I'll give you kind of the point for this one. Actually, did my iClicker just shut down? I definitely had it. Let's see if it yells at me. Okay, this shut down on me for some reason. So let's try this one more time. See if this pops in there. All right, there we go. So as long as you give me one of the two answers, right, that could theoretically be correct, but you can't rule them out, I'll still count the script. But if you want to have, I'll give you a little bit of time. If you want to actually work through and calculate the exact answer, I'll let you do that. That way you can identify any kind of issues kind of in calculating this. Okay. So we've got our test statistic equation, right? We're given the sample difference. We've got a sample variance. We had 40 card holders from the earlier kind of slide. So we've got our sample size is 40 here. And then assume true difference. Remember, our null alternative hypothesis was that it's less than 0. So we assume that it's greater than or equal to 0 for the null. Okay. So give you a little bit of time to work on this one, and we'll kind of talk about it. All right. So I'll try to wrap up here. 10, 15 seconds or so, and then I'll close it out. All right. If you haven't gotten an answer in, take your best guess. 22 people here today. All right, I'm gonna close it out. So which two should have you been able to rule out right away? Yeah, so remember, your test statistic, in this situation, it represents a t-value. Right? In other situations, right, maybe it's a z-value, but either one of those is telling you the number of standard deviations away you are from the assumed true value of the statistic you're interested in. We're interested in the sample difference, and so the assumed true difference that we had was 0. That was the value in our null alternative hypothesis, right? We found a sample difference of 2.1, right? So that has to be a certain number of standard deviations above the assumed true mean. So if it's going to be above that mean, it has to be positive. Right? The z value or the t value tells us the number of standard deviations above or below we are from that assumed true value. So here we found sample evidence that's above, so we know the test statistic has to be positive. Now from there, it's a matter of plugging things into our equation. So we had this, right? So it's really just a matter of what? 2.1 minus 0. I already forgot the variance. 64. And then sample size of 40, right? It's just a matter of getting this entered into our calculator. This assumed true difference value came from our null alternative hypothesis because we were assuming it was greater than or equal to 0. So we use that as kind of our cutoff point that we test. So I think if I do this, I'd probably end up with the one that's not 10. What was it, 1.44 or something like that? Or 1.66. Okay. So I'm thinking about if I was to plot my test statistic, it is nowhere near my rejection regions for a left-tailed test, which makes sense because I originally found sample evidence that supported the null. So I failed to reject at every level, right? Not even close. Any questions on anything there? Nothing? Okay with this? All right, so we're okay with that. I was going to do the suicide by county thing. And then I changed my mind last week, but this was the idea I had going into the semester. And I go in and out of being interested remotely on this, but I'm somewhat interested again. So I grabbed a bunch of the COVID numbers that the CDC puts out there. So, I mean, you should be somewhat reliable. So I'm going to just increase the views on these so that we can see them a little bit easier. And we'll work through a matched pairs example. Actually, I think I'll probably work through 2 of them. Right? We could do it in all 3 sheets, but I'm just going to do 2 for right now. So I'm going to go to this cases class variable. So what I did is I had this data on all these different counties, their populations, and then kind of their COVID numbers. So the way the data came in, I had to kind of figure out like whatever the change was from September to October, that was like the number of new cases, right? Excuse me, and then I divided it by that county's population and came up with, not this one. So 2020, I came up with the number of new cases per person in the county last October, and then, well, I said last October 2020, and then October 2021, right? I thought this might be interesting to like see, like, I mean, what was the main thing that happened between those two time frames? From October 2020 to October 2021, we had a vaccine, right? So you would think maybe that impacts the cases that we see. Right? So I'm going to go through and just find the mean difference in each county, right? So I've got this county's cases per person in 2020 and 2021 in the month of October. So I'm comparing like otherwise pretty similar months. And I'm doing the analysis like at the county level within each county. So I'll just simply take the average of this difference variable, okay? So Control Shift or Command Shift on a Mac, hit the down arrow, hit Enter. I've got the mean difference pretty quickly. And in practice, what you would actually have to do originally the data would come in like this, you wouldn't have this column where it says difference, right? So I would have to find this difference variable, which is simply take the new time period minus the old, right? And then to do that for every county, I could drag this down. But if I can get this to be this like thick plus black plus sign, if I double left click, that does it for every observation, right? Fills it all the way into the bottom. So it's kind of a nice handy little trick there. Right? And also, if you're on a laptop, another nice shortcut, if I hold Control Shift, not only is it great for selecting entire columns in a formula, it allows me to kind of navigate so I can get like back up to the top of my data set. Right? Or if I had like 100 variables here, Control Shift, hit over, sends me to the edge of my data set. So that's kind of nice. So I have this mean of this difference variable. The next thing I needed was the sample variance. So var.s, we've used that function before. Select this difference variable. And then my sample size is just going to be, use that count function. It'll count the number of observations I have. So I've basically got, right, here's my sample size n. This is my mean difference, or what we were calling earlier, d bar. So I could then start to do things like, maybe I want to do a right-tailed test. Right? So I've got this idea that, we can type it out in Excel here. I'll leave this over here for a second. So maybe my alternative hypothesis, I want to test for whether or not this mean difference is greater than 0. So I assume the opposite is true, which is that mean difference is less than or equal to 0. Being a little bit sloppy with my notation here. I don't feel like finding all the symbols, but you get, kind of see what we're doing here. We've got a right-tailed test. Okay. Well, I found a positive difference, right? Which actually would tell me that cases have went up over the last year, or at least on average per county. So I can go ahead, calculate my test statistic. So I'm just here, all I'm going to do is have Excel be a calculator for me. And I'll show you a shortcut afterwards, but for now, I'll just show you how do I use Excel to be a calculator for me. Okay. So I'm going to take that sample difference I found, subtract the assumed true difference of 0, right? Then divide by the square root of the variance I found, divided by my sample size. This should give me my test statistic. Okay. Now I could put this as a cell reference. It wouldn't really matter, but I'll show you something kind of in a little bit later as to why, why am I putting -0 in here? Well, just in case I did want to test against any other value than 0, I can show you how that would work. Okay. So I've got a huge test statistic. So apparently I have a sample difference that, based off my sample size and the variance that exists in this variable, it's very far away from that assumed true difference of 0. How far away is it, or how unlikely was it? Well, my p-value should be, for a right-tailed test, the area to the right of that test statistic. Well, I know that if I use these dist functions, and because I only have the sample variance, I should use that student t-dist, so t.dist. If I select my test statistic, comma, tell it my degrees of freedom, which is just my sample size -1, and then put comma 1, so I make it cumulative, it gives me the area to the left. Now, if I put a 0 in there, it does not give me the area to the right. I've tried to make this, when we're using these dist functions, you just always make it cumulative. You should always be putting a comma 1 there as the last thing. However, it was a right-tailed test. I did want the area to the right, not the left. So what could I do here? Simply, not absolute value. Be careful with that, right? Because, yeah, if we're looking for a t-value, then that absolute value would be fine because we're looking, same value on the other side. Here, we're looking for the area in the tail. So we've got this huge area to the left. So the area to the right would be 1 minus that. Okay. And we get a p-value of pretty much 0, which kind of makes sense. We saw something 46 standard deviations away from that assumed true difference. That probably means our assumed true difference of 0 is wrong. Right? We can reject at whatever level of confidence we want to. Okay. Now, the reason why I put a 0 in here, and it's not going to play out, I'll show it to you on the other example as well. It's not going to play out as well, is we have this shortcut, which is this t.test function. Okay? So if I use this t.test function, all I have to do, I don't have to do all the intermediate steps. I can tell it, okay, what's my after time period? Well, it starts here and it goes all the way down to the last observation. So I'll select that. The second thing I have to tell it, so comma, is the second variable or the before time period, which is over here. So I select that. Scroll back up so you guys can see this. Comma, the third thing is, how many tailed tests am I doing? Well, here I have a right tail test, so it's just one tail. And then comma, what type of problem am I doing? So on Monday when I filmed, so I posted the videos as two separates because when I tried to splice them together, my laptop video editing was not working and wouldn't do it for me. I'm going to retry that on my desktop computer tomorrow and kind of re-upload those as one video. But one of the things that I worked through was an Excel example for two population means where I had two different samples, right? And that was, we were using type 3 here. Well, here we've got the same counties, right? Just two different time periods. So we're doing a matched pair example. So we put a comma 1 as that very last argument in that t.test function. So what this will now do is calculate this difference variable behind the scene, find the mean difference, find the variance, calculate the sample size, calculate the test statistic, look it up in the student t-distribution, and spit back out at you the p-value. And if you put a 2 in here for a two-tailed test, it would also multiply the area by 2 and give you the p-value. Now, these are going to be 0, so you might not believe me that these give you the exact same thing. On the next problem we'll work through here in a second, we'll see that these p-values will always line up. The only problem is when I do the intermediate steps and I don't use this built-in shortcut, if I want to test against the value of 0, that's great. But maybe here I want to say, okay, is the changes in cases per person anything greater than 0.5%, basically, or 0.005? Okay. If I hit enter here, well, it's still pretty great. So maybe I have to make this a little bit greater. Still not great enough. Let's just say, can I say 0.007? There we go. All right. Now I start to get a p-value where I can reject at some levels, but not at others, right? Because I was playing around with that assumed true difference, right? I was using values other than 0. Okay? So I just want to show you can do that. Like, I'm not going to expect you to do that on the exam, but moving forward in practice, like if you do other stats courses or you're doing actual application of t-tests, you might want to do something that's not 0. Right? And the problem is, if I do the intermediate steps, I can alter that test statistic equation to test against values other than 0. But the built-in t.test, notice there's nowhere I can specify what value I want to test against, because the only value that it can test against is the value of 0. Okay? Which is kind of a pain, but that's the way the built-in shortcut kind of is. Okay. Any questions over anything there? Want to see a cell again, or a question about why something was done the way it was? Okay. So kind of interesting. I mean, obviously this is very limited. We want to do things like linear regression to account for other factors down the road. We probably wouldn't use this information and say, oh, in the past year, the vaccine's not doing anything, COVID cases have actually went up. And I can say that with a pretty high level of confidence, right? I actually found something that goes against the null here, which is that the difference is less than or equal to 0. So with 99.99% confidence, right, when I was using that assumed true difference of 0, I could say that I could reject that null, or I could reject that number of cases per person that actually went down, at least on average across counties. Okay. So I could do the exact same thing, but do the death percentage one. So I had the exact same kind of data here, but I have the number of deaths as well. So I just took the number of deaths, I had the number of cases over here. So I divided by the number of cases and kind of came up with like this death percent, right? What percent of people in the county who contracted COVID ended up dying, right? So I've got these two kind of death measures, right? And I can actually determine whether or not death rates have went up or down. So even if cases are going up, maybe the death rates have went down, right? People aren't as likely to get this disease as severely. So I've got that difference variable. I go through and I find the mean. I go through, use var.s to find the sample variance. I use my count function to get my sample size. This should be something that, we're getting pretty familiar with using those three functions. Okay. From there, it's a matter of using Excel to be my calculator. So that was where I said, okay, take the sample mean difference you found, subtract the assumed true difference of 0, divide by the square root of your sample variance divided by your sample size. Okay. Hit enter. I get a pretty low test statistic. I want to do a two-tailed test here. I think I went over this on that video I posted Monday as well, but kind of a nice shortcut for a two-tailed test. Instead of using t.dist, I can use this t.dist.2t. Okay. Now, one of the issues with this is if you have a negative test statistic, it only accepts positive test statistics here. Now, I don't know why. It seems like they could very easily write in to just take the absolute value of whatever test statistic you tell it, and it's a symmetric distribution, but it can only accept positive value. So if we had an example where the test statistic wasn't positive, we would have to use the absolute value of that test statistic. Okay. That doesn't change anything here. It's already positive, but just to make the point, comma, what's your degrees of freedom? And now here, it treats as a two-tailed test. It finds the area in that one tail and then multiplies it by 2 for you. So you've got our p-value is like 0.5. We can't reject the null at any level here. So here, maybe I set up that my null was that this true mean difference was equal to 0. Right? That would be my null hypothesis. I can't reject that. So I can't say that the death rates from COVID have actually changed at all across that October 2020 to October 2021. Okay. Any question? I know I went through that kind of quick. I'm just basically the same thing, but we're just using slightly different data here, which is kind of interesting. Like I said, we will talk about regression on Wednesday. In fact, I'll be putting up the very last Learn Smart assignment. So if you've done all of them up to this point and gotten all the points, if you don't do this last one, it would be the one that gets dropped. If you've missed one somewhere along the way, this is definitely not, you don't want to miss this one because then one of those zeros counts, right? So I'll get that posted when I get back to my office today. That'll be due before we meet in class on Wednesday, and it's the last Learn Smart, okay? Now I could also have done the built-in t.test here, right? So that was t.test. My first variable was the 2021 death rate, so I'll select that, comma, scroll back up here, select my second variable, which was the older time period, Control Shift, hit the down arrow, or Command Shift on a Mac, comma, the number of tails. Well, now I'm doing a two-tailed test, comma, and I've got a matched pairs example. So now if I hit enter, hopefully this should match up exactly with the p-value I found when I did all the intermediate steps myself. Sure enough, exactly the same p-value. Okay. So it's nice when your assumed true difference is 0, because you can just use this built-in t.test. If it's anything other than 0, well, now I have to actually calculate the test statistic. And maybe I wanted to do, I don't know, 0.005 or something, right? And so that t.test will never update. There's nowhere where I tell it the assumed true difference. It just is always using 0. Okay. Any questions on anything here? You want to see a cell again, or? So this will be kind of the last one on that current Excel assignment. So if we look at this courses page, nope, that's not our courses page. We're section 5. We've currently got a connect in Excel. So there's going to be one more Excel assignment. Once again, I dropped the lowest. So you can kind of almost, like if you've done the first 3, you can kind of pick and choose between doing the 4th or the 5th. I'll probably also put up a 6th homework for Connect. And the way that you can kind of treat that is, if you've done the first 5, you can kind of ignore it and just treat it as an additional study tool. That's the only really reason why I'm putting it up there. So it gives you an opportunity, if you've missed one, to kind of do the 6th one, and then, you should be fine. It gives you an opportunity to improve your grade, even if you've done all of them, but you did kind of poorly on one, or you only got half of it done. You do the 6th one, and then that lowest one will get dropped. But if you've done the first 5 and you feel pretty okay or comfortable with the grades you got in the first 5, you could not do the 6th one. It'd be a 0, and it's the exam, or it's the assignment that gets dropped. So it's the lowest of each type. Your lowest Excel will get dropped, your lowest Learn Smart, and your lowest Connect. So I'm kind of telling you there will be one more Connect and one more Excel. But if you front loaded your effort in this course, it's not like you need to complete all of these. We'll have some kind of assignments running concurrently. Okay. Now I probably won't put those up until after Wednesday because it'll be over kind of linear regression. But I just wanted to make you aware that those are going to be assigned kind of later this week and probably due at the end of next week. Okay, so we'll have a little bit shorter time to do them, but if you've already done the kind of previous assignments, it shouldn't be, you shouldn't have to worry too much about those. Okay? Yeah. Yeah, it's in the syllabus, the exact time. We have a time frame based off of the time that we meet to ensure that all classes can meet in their same room without having like time conflicts, right? We'll talk more about that probably beginning of next week, just kind of more of like the logistics of the final. Yep. Yeah, I'll probably call it the final exam, but it's like every exam has the ability to be 30, 20, or 10%, right? Yep. Any other questions for me before we get out of here? Yeah. Is anybody, I think, I don't know if I looked at this. So one person started, so one person was able to get it to work. I was having issues. Yeah. I will try to go in and redeploy it. And if you're still having problems with it, send me an email. Is it opening? Not? Okay. I'll go back to my office and redeploy it. I don't know why it's opening for me. So if for whatever reason after 6 o'clock tonight, if you try to open it, because I don't know exactly when I'll get it redeployed. After 6, if it's not showing up, please one of you send me an email so I can get it. I'll probably just like completely repost the assignment and like give it a slightly different name. That way it'll kind of, avoid whatever issue it's having. But I think if I redeploy it, it should work. Was that your question too? Yeah, for these 2 assignments, yes. Yep. After today, that was all you need to kind of do both of them. Yep. All right, we'll see you guys on Wednesday.